Welcome to EPG Pathshala. Today we will be discussing a thing which you have learnt in our undergraduate course, that how to place a few number of balls into few cells. It's not just like that the balls and cells, we have more conditions. For example, what will happen if balls are indistinguishable? What will happen if the cells are indistinguishable? So in total, how to divide or how to distribute the balls into different cells, that will be discussed in this module. So we call this as occupancy problem. And these results or the statistics come out of this problem are rigorously or widely used in physics. So we'll describe a few statistics which involves the results corresponding to this occupancy problem. So the main objective is to how to distribute say n number of balls into r cells or r number of balls into n cells, whatever it may be. So we'll be finding the counting procedure, how to partition the total number of balls into different groups such that we can have the restriction that all the cells will be occupied, or we can have the restriction that we can have that each cell can contain 0 balls or more than 1 balls. So all the conditions will be examined. The first case, when the boxes are indistinguishable and balls are indistinguishable, then if the balls are distinguishable but the boxes are indistinguishable, so all possible combinations will be discussed in this module. Occupancy problem is very popular in statistics. We have learned this in our undergraduate courses, but today we will discuss it once more. The occupancy problem is about the problem of randomly assigning a set of balls into a group of cells. So we will have some cells and we have a set of balls. Now one may ask the question, in randomly placing r balls into n cells, what is the probability that exactly j cells are occupied, where j ranges from 1 through n? That means what is the probability that one cell will be occupied, what is the probability that exactly 2 cells will be occupied, and so on. And we can answer this question after learning counting techniques that will be discussed. To make our life much more simple, we start with the example that suppose we have 7 balls and we have 6 cells. 7 balls and 6 cells. Now the problem is that we have to place these 7 balls into 6 cells. So we can view this problem as a problem of placing 7 balls into n equals to 6 cells as rolling a fair die 7 times, because we know a die has 6 faces. So cells are there assumed to be face value of a die. Each roll of the die is essentially placing a ball into one of these 6 cells. Thus the rolls of the die can be considered balls and the faces of the die can be considered cells. In this example we have 6 cells and 7 balls. Each roll of the die can also be viewed as selecting one face out of the 6 faces. And the occupancy problem of randomly assigning r balls into n cells is same as selecting r objects with replacement out of n distinct objects with replacement, because one cell can contain more than one ball. So the question we have, how to partition the whole population into k subpopulations. So we say the theorem, let r1, r2, r3, rk be such integers such that sum of all these ri's equals to n. So r1 plus r2 plus r3 plus rk is n, and all ri greater than equals to 0 for all I belongs to 1 to k. Ri greater than equals to 0 means any cell can contain no ball or more than 1 balls. The number of ways in which a population of n elements can be divided into k ordered parts. We say partitioned into k subpopulations, of which the first contains R1 elements, the second contains R2 elements, the third contains R3 elements, etc., can be expressed as n factorial over R1 factorial into R2 factorial into R3 factorial into Rk factorial. So this is the theorem we have, how to divide the subpopulation into, how to divide the whole population into k subpopulations. The proof is not very difficult to understand. In order to effect the desired partition, we have first to select R1 elements out of the given n. So what we are doing, first we are taking R1 elements from the population of size n. Now once they are allotted, we have n minus R1 elements left. Now we have to put R2 elements out of these n minus R1 elements in the second group. So once we do this for first group and second group, now we are left with n minus R1 minus R2 elements. Now out of these n minus R1 minus R2 elements, what we are doing, we are taking R3 elements for the third group. So after forming this k minus 1 group, we will be left out with n minus R1 minus R2 minus Rk minus 1, that is nothing but Rk. So this many elements are there and these form the last group. Now if I product all these choices, nc R1, n minus R1 c R2, n minus R1 minus R2 c R3, and so on, and lastly we will have n minus R1 minus R2 minus Rk minus 1 c k Rk minus 1, and if we do this manipulation, we will be left with n factorial over R1 factorial into R2 factorial into R3 factorial into Rk factorial. Thus we prove this theorem, where we say that how to divide the whole population into k subpopulation where each group can contain more than one elements. These numbers are called multinomial coefficients. Since they are the coefficients in the expansion, if we do the expansion of x1 plus x2 plus xm to the power n, then this coefficient will come. Now if you use this theorem and we want to know how to divide the 7 rolls of a die into 4 subgroups, we may say that one group consisting of one roll of 3, one consisting of one roll of 4, one consisting 2 rolls of 5, and one consisting of 3 rolls of 6. Note that if you remember the phase values, not all phase values I am considering right now. So what I am considering? One roll of 3, one roll of 4, 2 rolls of 5, and 3 rolls of 6. And if we use this result, we will have 420 possible orderings. How to get this 420? It will be 7 factorial because I have n as 7 and R1 is 1, R2 is 1, R3 is 2 and R4 is 3. So I don't have R5 and R6, so they are all 0. So in total we will have 420 possible orderings. The occupancy numbers help us sum out the order of the balls within the cells, and order of the cells still remain in the occupancy numbers. So consider the occupancy number set 0, 0, 1, 1, 2, 3. Why this is so? So in the whole example, 2 faces they are not appearing, one face appearing once, another appearing once, another appearing twice, and another appearing thrice. So we wish to divide the 6 faces into 4 subgroups. One group consisting of 2 faces that do not appear, one group consisting of 2 faces, each face appearing once, one group consisting of one face appearing 2 times, and one group consisting of one face appearing 3 times. This is another opportunity to apply the above theorem, and if we apply this theorem, we will have 6 factorial over 2 factorial into 2 factorial into 1 factorial into 1 factorial, that means 180 ways. So in total there are 420 into 180, that is 75,600 different orderings of the 7 rows of the die generated from the occupancy number set. The set is 0, 0, 1, 1, 2, 3. And if you consider the total number of outcomes, it will be 6 to the power 7, and this number is 279936. And out of this huge number of outcomes, from rolling a die 7 times, 75,600 of these are from the event that 2 faces do not appear, 2 faces appearing once each, 1 face appearing 2 times, and 1 face appearing 3 times. So using the theorem that we have just mentioned, we can compute the sum in this way. Consider another example. We want to permute of n balls, and the balls are distinguishable by groups. So suppose there are R1 balls of color number 1, R2 balls of color number 2, RK balls of color number K. Their colors are distinguishable, but balls of the same color are not. So whenever I am talking about color number 1 R1 balls, these R1 balls, they are indistinguishable, but these R1 balls can be distinguished from the R2 balls which are of color number 2. Once again, the R2 balls, all the balls are indistinguishable. So the balls of the same color are not distinguishable. Here also we have this condition that R1 plus R2 plus RK equals to n. So in total we have n balls. The total number of distinguishable arrangement of these n balls are n factorial over R1 factorial into R2 factorial into R3 factorial into RK factorial. So this is an example where we have applied the theorem we just mentioned and proved. Now consider another example. A throw of 12 dice. So we are throwing 12 dice together, and that can result in 612 different outcomes, to all of which we attribute equal probabilities. The event that each face appear twice can occur in as many ways as 12 dice can be arranged in 6 groups of 2 each. So 2 plus 2 plus 2 plus 2, so 6 2's equals to 12. Hence the probability, if we follow the frequently this definition, it will be 12 factorial over 2 factorial to the power 6 divided by total number of cases, that is 6 to the power 12. There is another example I want to mention. There is a game of bridge. So at a bridge table, the 52 cards are partitioned into 4 equal groups, and therefore the number of different situations is 52 factorial over 13 factorial to the power 4, because we have 4 different types and each type contains 13 cards. So in total, the total number of arrangement will be 13 factorial to the power 4, and this is a huge number. It's 5.36 and so on into 10 to the power 28. Let us now calculate the probability that each player has an S. So we know that there are 4 S's, and these 4 S's can be ordered in 4 factorial, that is 24 ways, and each order represents one possibility of giving 1 S to each player. So we are left with 48 cards, and these 48 cards can be attributed into 48 factorial over 12 factorial to the power 4 ways, because we are excluding the S from the set of 13 cards. Hence the required probability will be 24 into 48 factorial into 13 to the power 4 over 52 factorial. Now we will come to the occupancy problem. Placing randomly R balls into n cells. R balls can be put into n cells in n to the power r possible ways. How? Take the first ball. You can put the first ball into any of these n cells in n ways. Take the second ball. Once again, you can put the ball in any of these n cells in n ways. So for the first 2 balls, you have n square possible ways. Now take the third ball, then we will have n cube possible way. So in total, if you have r balls, the possible ways can be n to the power r. The most important properties of a particular distribution are expressed by its occupancy numbers R1, R2, Rn, where Ri is the number of balls in the ith cell. Note that R1 plus R2 plus Rn is equals to R, total number of balls, that is R. Once again, each cell can contain more than one balls or nothing. So Ri can be greater than equals to 0. And we treat these balls as indistinguishable. We cannot distinguish these balls. And the distribution of these balls is then completely described by its occupancy numbers, because right now the balls cannot be distinguished. Under this setup, the number of distinguishable distributions, that is the number of different solutions, is n plus r minus 1 choose r, which is same as n plus r minus 1 choose n minus 1. Now if we put another restriction that all cells will be occupied, in that case number of occupancy number sets with all cells occupied will be r minus 1 choose n minus 1. Now how to prove these two results? Consider the rolling of the die 7 times. We have already discussed this example, r equals to 7 and n equals to 6. And if you consider the occupancy number set 1, 0, 1, 0, 2, 3. So we can represent this occupancy number set with bars and stars. Now to have one cell we need 2 bars. So to have 6 cells we need 7 bars. So here I have 7 bars. Now you consider the balls. The balls are represented by star and the space between 2 bars is a cell. Now the set we are considering, the occupancy number set is 1, 0, 1, 0, 2, 3. That means in the first cell there will be one element, in the second cell there will be none, in the third cell once again we will have one ball, in the fourth we don't have any, in the fifth we will have 2 balls, and in the last cell we have 3 balls. So this is the setup corresponding to the occupancy number set 1, 0, 1, 0, 2, 3. Now for n cells we need n plus 1 bars, and this can create n spaces representing n cells, and such a representation begins with a bar and ends with a bar. So the first bar and the last bar we can't change, so we are assuming this to be fixed. Now we are left with n minus 1 bars, and these n minus 1 bars I can change, and if I change the position of these bars I will be getting new and new arrangement of the balls. So such a representation begins with a bar and ends with a bar. In between the 2 bars on the ends there are n minus 1 bars and r stars. So in total we will have distinguishable distributions equals the number of ways of selecting r places out of n minus 1 plus r. So n minus 1 corresponds to the bars and r corresponds to the balls. Thus the number of occupancy number set is n plus 1 minus 2. This minus 2 is for both n bars which we cannot move. So we will have n minus 1 plus r choose r, that is nothing but n plus r minus 1 choose r is equivalent by saying n plus r minus 1 choose n minus 1. For the case of all cells are occupied, if we put that restriction by at least one ball, first we have to place one ball into each cells. So if there are k balls or r balls and we know that each cell will contain one ball, then we are left with r minus n balls. Then we can place the remaining r minus n balls into n cells, and this can be done using previous theorem. R minus n plus n minus 1 choose n minus 1 is same as r minus 1 choose n minus 1. In our example we are talking about of rolling a die 7 times. There are a total 6 to the power 7 possible orderings of the 7 rolls, but there are 7 plus 5 choose 5, that is 792 occupancy number sets, of which 7 minus 1 choose 6 minus 1 is equals to 6 have all cells occupied. So if we put the restriction that all cells are occupied, then we have number of arrangement as 6, but if we don't have any such restriction then the number of arrangement will be 792. Now these occupancy problems, based on these occupancy problems, physicists they have used this in their research. So there are different types of statistics they are using. The first one is called Maxwell-Boltzmann statistics. So here the balls are numbered 1, 2 up to k, and the sample space is the set of sequences A1, A2, AK with all the AIs lies between 1 to n. The second statistic that they are using is called Bose-Einstein statistic. Here we have changed the condition that balls are indistinguishable. So thus the sample space is just the number of balls in each urn, the set k1, k2, kn, such that sum over ki is equals to k. The third one is called Fermi-Dirac statistics, and so here we have the condition that no more than one ball can occupy a given urn and the balls are indistinguishable. So in physics, k photons arrange themselves so all such configurations are equally likely. If we consider the example where n is equals to 2 and k is equals to 2 also, then the arrangements 2 plus 0, 1 plus 1 and 0 plus 2 each have probability 1 over 3. This is from Bose-Einstein statistic. This is different from Maxwell-Boltzmann, modeled on assigning 2 photons one at a time to 2 energy levels. In the latter case, 1 plus 1 has probability half. Photons, called bosons, cannot be distinguished from one to another, so they are indistinguishable, and this partition counts as only one case physically. So after considering all the possible arrangement between cells and balls, in a nutshell we can represent the problem in this slide. So we have the conditions: are distinguishable balls or are indistinguishable balls. Regarding the boxes, they are distinguishable boxes or indistinguishable boxes. So I am assuming first the simplest case, balls they are distinguishable, boxes they are also distinguishable. Now if we consider that we allow that one box may remain empty, then the total number of cases will be n to the power r. But if we put the restriction that no box empty, then the number of choice will be n factorial, and we are using a symbol. This symbol says that r within the brace n is number of n subsets of r balls. So r n within the braces, this is by definition it is the same as the number of n subsets of r balls. So if no box is empty, total number of cases will be this. Now if we just relax or we just impose the condition that the balls are indistinguishable but boxes are distinguishable, then total number of cases for the first one, when we are allowing empty box, is r plus n minus 1, choose r, and if we put the condition that no box can remain empty, it will be r minus 1, choose n minus 1. We have proved these two results. Now we just shift, or we just think about the situation where the balls are also indistinguishable. Now if balls are distinguishable but the boxes are indistinguishable, then if we consider this case that empty box can be allowed, then total number of possible cases will be sum over I from 1 to n, braces r, c, r brace I, that means I subsets of r balls, and you have to sum over all possible such partitions. Now if we put the condition that no box will remain empty, then it will be once again within the braces Rn. So this is the same as the number of n subsets of R balls. Now if the balls are also indistinguishable like the boxes, then if we allow the empty box, then it will be sum over I from 1 to n, and we are using a symbol Ri within two straight line. This is nothing but a number of partitions of R into n parts, and what we are doing, we are to summing up all possible such combinations. But if we put the restriction that the no box remain empty, then it will be once again the same symbol R and n. Now to make understand of these symbols, we can take one example. For example, if take R equals to 4 and N equals to 2, then the partitions are, we can have 3 plus 1 or we can have 2 plus 2. So within two straight lines, 4, 2 is 2. The partition 3 plus 1 says put 3 balls in one box, in one in another. So this slide will give the whole concepts of occupancy problem in a nutshell. In this module, we have learned how to find the number of possible ways or different arrangements where we can find or we can distribute a few number of balls into few number of cells, and their applications are also mentioned, especially in case of physics. And in a nutshell, we have described all possible combinations of this distinguishable or indistinguishable balls as well as distinguishable or indistinguishable cells. So all possible cases have been discussed, and this will give a complete idea of the occupancy problem. Though there are few generalizations of this occupancy problem, but they are beyond the scope of this module.